Today we're going to be talking about some USACO Platinum topics. Um, they're just okay. So this is like the first thing I'm going to say, but essentially, like Platinum covers essentially all of what programming can cover. Almost every topic to a certain extent is fair game. So there's no possible way I could talk about everything or even mention everything that is required for Platinum. It would just take way too long and it wouldn't be a great use of our time. So I'm just going to be talking about some of the most interesting and most common topics that have appeared and probably will appear in the future. Um, I also didn't talk about many of the other topics that you might have learned in gold. Like, for example, dynamic programming is one of the most common topics in platinum, but based on what I like, what I've seen, many of the techniques you need to know beforehand for like things like dynamic programming, those are like those techniques you've already learned about all of them when you've done gold. And so I'm not going to talk about them now. In Platinum, a lot of dynamic programming problems involve a lot more thinking, and this thinking is something that no one can teach. You have to learn it from solving a bunch of problems and learning what's best for you. So, yeah, with that said, let's get into the two topics I've prepared today. First topic is range queries. So, a range query is essentially like if you remember in gold, a binary index tree solves range sum queries. So a binary index tree is a way to solve range queries. But binary index trees aren't very good. First, because they're very limited in what they can accomplish. And second, because they don't they don't cover a lot of like different situations. So for example, what I mean by this is binary index trees don't cover many operations. You can really only use addition and XOR for binary index trees. However, uh, many problems will ask you for minimums, for maximums, maybe even something else, like maybe there's no updates, but the operation that you need to do is really complicated and you don't have that much time. And so you need to basically find better ways of being able to solve range queries, which we'll talk about here. So the first improvement on binary index trees is segment trees. So a segment tree essentially is adapted around the same idea of a binary index tree. So essentially a segment tree looks like this. So as opposed to a binary index tree, which contains everything, or as opposed to a binary index tree, which I'll point to the ones that a binary index tree contains. A segment tree contains everything. And this allows the segment tree to do a lot of the things that a binary index tree cannot do. So all of this text is basically how you would implement this. So if the index here is IDX, then the child is 2 times IDX. The left child is 2 IDX, the right child is 2 times IDX plus 1. And this corresponds to L to M. This corresponds to M plus 1 to R. So yeah, basically it would correspond to something like this. Each node has one value or many different values, and the values inside the node correspond to the operation over the entire range. And then we can do updates and queries in this pretty quickly. In update, you just need to update. So like, let's say you want to update this one, then you would update starting from the base node. Then you would find which half you go to. Then you would find this half is where it is contained. You update this half, and now you use the updated versions of the left half and the right half to combine them into the new version of this. So yeah, and then you keep doing that until you've successfully updated. And a query goes down like, so let's say your query is from here to here. A query basically goes down until you found or until you found a range that's completely contained within it or completely contained out or completely outside of it. So for example, let's redraw the segment tree. Let's say your query is over here. So what you do is you start from here. Then you go down both of these. So you check this. This is completely contained. So you add this to your answer. Now you go down here. This is not completely contained because some of it is inside and some of it is outside. So you go down both of these. So it goes down here and here. Here, this one's completely contained. So we add that to our answer. And this is completely outside. So we just discard it. So at the end, we'll basically be summing this and this. And yeah, both are done in O of log n. The proof is fairly simple, but so basically the depth is log n, the depth of the tree is at most log n, which is fairly intuitive. And the query, basically it's kind of like how binary works, where it'll be 2 to the k plus dot 2 to the something minus 1, and then basically the time complexity is basically the maximum k, and in this case the maximum k is at most log n. So yeah, that's basically how basic segment trees work. I went through this fairly quickly with the assumption that you guys already know most of what seg trees do. So I'm going to be more focusing on what you can do with seg trees rather than what seg trees actually are. Yeah. So another modification of a segment tree is a lazy segment tree. So a lazy segment tree is basically it's a way to do range updates without like having multiple segment trees. In the same way, like if you do range updates with binary index trees, you would need multiple binary index trees. In a segment tree, you can just use a lazy value on each node to basically update an entire range. So how would this work? Well, let's redraw the segment tree. So the basic idea behind this is that at each value, you keep the actual value, which usually is like seg or whatever you want to call it. And you also keep a lazy value. So you keep two values. So at the start, the lazy values are all 0 and you build the seg tree values to whatever it is. When you do a lazy update, you're essentially kind of doing a query. And what do I mean by that? You're doing the same thing as you would do in a query, except so let's say we did this, and once we find which ones are completely contained here and here, instead of just adding that to our answer, which we can do with a query, we can instead just lazy. We can just do lazy plus equals to whatever value, like the update value. And then here we can also do lazy plus equal to v. And after we have set these lazy values, what we can do is whenever we visit any node, like let's say we're visiting a node, let's say it's this node, right? And you check its lazy value equals to v, right? Then you basically, you don't want the lazy value anymore because like it doesn't contribute to your answer. You want to essentially relax the lazy value so that it's included in the node already, and then pass the lazy value down to its children. So here, when you're visiting this node, you basically you want to make lazy equal to 0. Lazy plus equals to lazy. And then at the end, lazy equals 0. So this guarantees that your segment tree will always, or this guarantees that inside the node that you're visiting, the lazy value would be 0. And a 0 lazy value means that there's no like updates we still need to make to that node for the information to be up to date. So we know that the information inside the node is correct. So yeah. Yeah. So there's a lot of applications of a segment tree. There are various ways to modify your segment trees. I think doing a lot of segment tree modification problems is very helpful because even if you haven't like seen that specific modification, it can help you a lot. For example, this is one of the most common problems that people will reference when they consider like seg tree modification problems, where you add extra information to your segment tree, and what that extra information does is it can essentially allow your segment tree to do much more complicated, much more sophisticated operations. You can check that out later. I'll send the link in chat after the thing. But generally, like I'll just give an example of a modification to a segment tree that has appeared in USACO before. So there's a type of segment tree called an activation segment tree, where essentially you can activate or deactivate nodes within the segment tree. So you have the update function, the query function, and you want to activate or deactivate a node, right? Activate a node. And the way this works is you just keep an extra array of like active. So that basically keeps track of whether that node is active. And then whenever you do an update or a query, you only find the answer on the updated nodes. So in your segment tree, your seg is going to contain all of the, your seg is going to like contain all of the active nodes, or yeah, it's going to contain the answer over all of the active nodes. So you don't have to do any extra work for your update or query. For range or update, it makes it a lot more complicated, but it's still the same thing if you think about it. But when you want to activate a node, you need to update all of the things that it's in, and you can do that by, it's actually fairly simple because you can just update the last one. It's essentially like another update function, but it's just an example of, you know, how different types of modifications can help you solve different types of problems. So that's the first big, you know, application of segment trees, is that you can change your segment tree in some way so that it can support very complicated operations like activating nodes, or in the case of seeding, I think it was like finding the first K that are empty or something like that. And it can be really effective. Another common way that segment trees used, well, there are many other common ways, but another common way is, let's say you have a 2D problem involving points and lines, and it doesn't have to necessarily just be points and lines. You could have like the problem is asking you, oh, hey, Farmer John is drawing this thing, and you want to find the number of intersections or something like that. Even this kind of problem can be done really easily with a segment tree. And like, let's say they're giving you a bunch of directions. You don't think of the directions as, oh, you process them sequentially. No, 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 no. You basically want to think of each individual line segment each time they change direction as a separate object. And once you do that, you can easily find that if you process, like, let's say your line is here and you're sweeping this way, you can find that each vertical line corresponds to a query, and each horizontal line corresponds to an update. And this allows you to solve a lot of different two-dimensional problems involving lines and how many intersections, how many different figures, all of that kind of thing. It just allows you to do all of that. And it also allows you to solve 2D problems relating to points. And the way it does that is like, for example, you go here, 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 here. There's actually an example problem that I'll show that involves this. But essentially, the idea is if you want to find like some of them are query points, this is a query, or this is an update or whatever, right? You can still use a sweep line technique to use a segment tree. So let's say you want to find the minimum Manhattan distance between any pair of these points. This is actually a pretty common problem, but essentially you split. So the minimum Manhattan distance is a formula involving an absolute value of xi minus y, or xf plus yi minus yf. This directly is really difficult to find the minimum of. But if you think about it, let's say this is your query point, you can once you split it up into an absolute value. Once you do that, let's say in one quadrant, it's xi plus yi minus, then this should be I. So you group when you're processing the query, and these you can put in your segment tree to find the minimum of. So this is just another example of a way to use segment trees on a two-dimensional plane to essentially solve problems relating to points and lines. Oh, there was another example, but anyways, yeah, those are just some examples of how you can use segment tree on different things. And like, even in those two-dimensional cases, it might not even be a case of they're giving you two-dimensional points and you need to find this. They might be giving you like different items with a property, and that property allows you to, or that property can be mapped as like a point on a 2D plane, and you can use certain properties with that to use a segment tree or whatever. Like, it's a very common thing that people will use, and it can be a lot of help to master it. So I recommend you look at a bunch of these types of problems and see all of the different tricks involving segment trees. Oh, yeah. The last example I wanted to give about an application of a segment tree is a really clever example where you're able to essentially create a graph, or like mimic like n squared edges using a segment tree. So let's say you wanted to have something like this, or so let's say you wanted to draw a graph. So you had this, except the way you draw the like edge by edge, this node connects to, and you basically want to find whatever on this to do this. And the idea is, let's say you have a segment tree. I'll draw it in terms of a tree instead of a range. So this is your actual array. These are your actual vertices, nodes. And then let's say you want to say that this node, you want to connect it to this range of nodes. Well, instead of directly connecting all of them, we can create a new node, which is the node like with index edge or whatever. And then you can connect it to all of the like the nodes that, like, we do a query here, and then we find that these are the nodes that we're aggregating, and the nodes that we're aggregating, we just add an edge over here. And it turns out that this is sufficient to be able to mimic the actual tree. So each query adds log n edges, or each like addition of edges adds log n new edges. So m log n. And so, for example, if you do a Dijkstra's on this, like so much more, add all the edges directly. So yeah, it's another cool trick that you can do with segment trees. Yeah. Is there a slide before this? No. Okay. The next thing I wanted to talk about was not segment trees specifically. It's another technique that you can use to solve range query problems. Divide and conquer is actually a very, very common strategy within Platinum. It appears in a variety of different cases. I'll show you a version that involves trees in our tree section, but let's stick over here. And there's also another dynamic programming optimization, which is really clever, that uses divide and conquer. So yeah, but for now, we're going to talk about how divide and conquer can help us solve range query problems. So the type of problem that you would consider using divide and conquer on is if you definitely do not have any updates. If you have updates, it could work, but it's generally not going to be as efficient as a segment tree, because updates will generally always add a factor of log n to your answer. And divide and conquer, when it's the most efficient, is processing queries offline. So we're going to be considering a case where, let's say you don't have any updates, but the operation that you're doing to combine the ranges is so complicated that the operation itself will take enough time to make a seg tree not work. So now we basically want to get rid of the log n. We want to, let's say the operation takes t of n time. Let's say that q times t of n times log n, which is the amount of time that it would take a seg tree to run, doesn't work. Instead, you need something that's like n t of n log n plus q t of n plus q log n. So this is the kind of case where you would want to use divide and conquer instead of a segment tree. And the way this would work is that let's consider you have a big array, right? And you already know all of the queries that you're going to do. So you're going to have a query from here to here, a query from here to here, a query from here to here, and a query from here to here. Like, this is just an example. Yeah, and then so divide and conquer, the idea is you basically split the array in two, this is through the middle, but you don't solve for to recursively go on each half separately. So the time complexity would be t equals to O of n, or O of n times whatever, plus the left half, which is, and the right half. So t of n, t of n plus 2t of n over 2. Yeah, and then this form is basically, or O of whatever. Actually, no, it has to be O of n, something like times n. This form is always going to be O of n log n. So this is why divide and conquer can help us do that. And this can be seen pretty easily. Like, you have n over 2, n over 2, n over 4, n over 4, n over 4, n over 4. And then the number of layers, like k layers, k is at most log n. So it's n log n. But anyways, the idea behind divide and conquer is to essentially split it in two and then like recursively do the left half and the right half, and then also solve for everything going through the middle. So in this case, we would basically want to solve for everything going through the middle. And how do we do that? Well, instead of doing a segment tree where you would have to add up log n halves, with this, we can do a prefix sum. So we do a prefix sum this way and that way. So essentially, once we figure out a prefix sum, the prefix sum represents the range from like here to like here. And then we can use that combined with the prefix sum from here to like here. And this would allow us to find the query from here to here. So for example, with this first query, we'd go from the middle to this end, and then from the middle to this end. And then when we find the total thing, we can just combine these two numbers, and then you get our answer for this query. And now when we have a query like this, which is completely contained within the right half, we can basically remember the queries that we haven't done, and we know which half it's in, and basically process the query in a smaller array. So this is the right half of the array, and then you split it in two, and then you do the same thing again, and then, yeah. And this achieves this complexity because n(t) of n log n is from the prefix sums. So this is the prefix sums, p sum. This is from answering the queries. And this is from, oh yeah, this is from basically figuring out which half the queries are in. So figuring out which half the queries are in. Yeah. Oh yeah, I also have another note. This and this could be different because like, for example, if you're merging two massive like conglomerates of objects, right? That could be very, very different from merging like, yeah, that could be very, very different from merging one object to a bunch of objects. So this one is merging one to a bunch. And this one is merging bunch to a bunch. So in a segment tree, you would only have this time. But let's say this time is substantially bigger than this time, right? If that's true and there are no updates, then you would really want to use that divide and conquer, because it can help you save a bunch of time from the time that you're losing merging a bunch of things together rather than merging one thing to a bunch of things. So yeah, that's essentially divide and conquer and how it can be used to solve static range queries. Are there any questions about this? Okay, I'll just keep going on now. The next thing that we'll talk about is square root decomposition. Square root decomposition in and of itself doesn't really show up that often, but the idea of square root decomposition can be applied to a lot of different things. So square root decomposition in and of itself is just where you have an array and you split it up into a bunch of blocks. Each block will have size of square root n. So you'll have at most square root n blocks. So if you have square root n blocks and square root n size for each blocks, then sometimes you can achieve a time complexity of O of square root n. This is generally not the most common way to solve a problem, because it's just really hard to like have a situation where a segment tree wouldn't be able to solve a question that square root decomposition would. But the idea of square root decomposition is something that is very prevalent and also very commonly used. So I'll just talk about a couple applications of this idea. One way you can do this idea is, let's say that you have two variables, k and I don't know, q, right? And this can happen in a lot of situations, but if you have k is small, like for example, k equals to the maximum occurrence, or no, not the minimum occurrence. Minimum occurrence, and q is the number of different values. Then you have the relationship q is proportional to 1 over q. K is proportional to 1 over q. If you have something like this, and you can devise of two algorithms, let's say one is k squared and the other one is q squared log q, or log n, or whatever, you can combine those two algorithms together to achieve a time complexity of, I believe, square root n square root n log n. Wait, no. No. What am I thinking? You can achieve a time complexity of n square root of log n. And the way you can do this is essentially, if k is less than or equal to square root n, then you use k is less than or equal to square root n, square root of n log n. You use this one. But if k is, but otherwise, then k is greater than or equal to n log n, so, or square root of n log n. So that means q is less than or equal to root n over log n. So that means that you use this one, and then basically the balancing act is trying to get the two time complexities to be the same. And once those two time complexities are the same, then you basically have the lowest possible time complexity, which in this case would be n square root of log n. And it can be very powerful, because if you think about it individually, a k squared algorithm individually, that's n squared. A q squared log n, that's n squared log n. Both of them are very, very bad algorithms, but if you combine them together, you suddenly get an algorithm of n root log n, which is really, really good. So yeah, that is one application of square root decomposition. Another common algorithm using square root decomposition is MOHS algorithm. So MOHS algorithm is essentially like an algorithm where you have basically you can have like a value function, and let's say value of LR, right? And you want to calculate value of LR for a lot of different L and R. However, your easiest way to calculate this is by finding from value LR, you can go to L plus minus 1 R, or L R plus minus 1. You can't really do you can't really directly calculate it. You can't really use a segment tree or something like that. So how do you do this? Well, again, we want to visualize this as a two-dimensional grid. So let's say we have a grid of n values each, or n by n grid, right? L and R both go up to N, and you have Q queries. So now what we can do is we can plot each query on the grid. Again, so plot each query on the grid. Now, this is the cool part where basically what we can do is we can separate them into square root n blocks. Now, we look back at what each of these means. One of these means a horizontal movement, so horizontal movement, and one of these means a vertical movement. So what we can do is we can start from the top, like we can start from the top left, and then we can keep going, or no, we can basically keep going down, start at the top left, keep going down, and then we solve that, and then we keep down, and then it's help us. Well, let's calculate the time complexity. Time complexity of n squared n already. However, we go horizontal root n times at most per query. If you think about it, each query, so we're having q root n there. But there is no other factor in our time complexity. So this is just our total time complexity. And that allows us to basically, in an offline way, solve this in square root n time per query, which is very, very, it's very, very cool. If you have an extra log factor, you can also get it to be square root log n as well, which is even better. And yeah, so yeah. And yeah, so practice problem. No one's here, so I'll just go over the solution to this practice problem. So basically, the idea is, again, we want to plot everything on a 2D grid. In a lot of these problems, plotting on a 2D grid is very, very useful. So that is another trick you want to keep in mind. So plot everything on a 2D grid. And you realize that some of them are queries and some of them are updates. Like they're defined in the problem that way. So if we do a sweep line, like this is our line and we're sweeping this way, what we can do is at each query, we can define a quadrant. And in each quadrant, we can separately solve for the answer in that quadrant. And then we can aggregate all of those quadrants together, each query, like for each query at the end of the whole thing. So how do you do this? Well, as I mentioned earlier with the Manhattan distance example, this problem is essentially also just finding the minimum Manhattan distance plus like a little distance that's defined by the slingshot. So what we can do is with each update, we can basically add d minus x minus y, I think. And for each, we find the range queries and then or a plus bi portion. And then we can do the same thing for each of the other quadrants. And once we do that, we can have a final answer for each query. And yeah, that's basically the example. Yeah. So the next topic we're going to be talking about is tree algorithms. What is happening? So the first thing that you usually do in a tree, or the first thing that you, or the most basic thing that you almost always have to calculate when you have a tree problem is the lowest common ancestor. So there are many ways to find this, but the two main ways are binary jumping and Euler tour. Generally, binary jumping is more code friendly and more fun to code also and much better. So that's what I'll teach. But binary jumping is always O of log n, and Euler tour, if you really put in the time and the effort, you can get it to find LCA in O of 1. So if you really are in a pinch for time, maybe do Euler tour, but yeah, I think binary jumping is probably the way to go. But yeah, so binary jumping, the basic idea is that in a tree, let's say this is your tree, you basically want to find the parents of each node, but you want to find very specific parents. In this case, you'll find the 2 to the ith parent. So let's say this is node X. What would that mean? Well, par 0 would be this node. Par 1 would be this node. So par 0 would be this node. Par 1 would be this node. And par 2 would go outside. So it would be an imaginary node, which is the parent of this node. This is part 2. And generally with an imaginary node, you can put -1, you can put 0 or whatever, and it'll still work. So the idea behind this is that first, calculating part 0, basic DFS, we all know how to do that. Calculating part I, we can use this formula. And the idea is you've already calculated all of I minus 1. So you go like from 0. So you go up 2 to the I. So up 2 to the I. And then here you go up another 2 to the I. So 2 to the I plus 2 to the I is 2 to the I plus 1. So this is basically this formula. And then after we've done this, we can essentially, or we can calculate the LCA very, very quickly. So is this, you want to find the LCA? The first step is to make sure that all of their depths are the same. This can be done by basically going from big power of 2 to small power of 2, and then relaxing. It would just go directly here. Depth, you essentially keep relaxing it. You go down, you go decreasing I, you keep relaxing it until you keep relaxing it as long as it's different. And then at the end, you do par A0 as the answer. So yeah, fairly simple. Yeah. Okay, so the next thing that I'll talk about is okay, so the next thing that I'll talk about is tree diameter. So what is a tree diameter? Tree diameter is essentially the maximum path length that's within the tree. So here the tree diameter would be like this or like this. It doesn't really matter which one you choose. And the diameter of the tree has very nice properties. So let's say this is X and this is Y. And these are the endpoints of our diameter. It doesn't matter which diameter we choose, but as long as these are the endpoints of our diameter, we'll have like, let's say any random point within here. Now we know that one property of a diameter is that the maximum distance between this node and any other node must be one of the endpoints of the diameter. First of all, we consider where other nodes are on this line, right? We know that if we number these 0, 1, 2, and then we start 0 on the other side, and then when we converge, like these numbers represent the maximum possible height that you can obtain at that vertex. So here, if we have like any node over here, then of course we want to go through a certain stretch of the diameter and then go out afterwards. But if you go out, let's say here, the maximum height possible is 1. And the maximum height is 1 because if the height were different than 1, like 2, then that would be our actual diameter. And this wouldn't be the real diameter because that length is longer. So let's say you want to go out over here, right? You want to go out over here. But that means that like the one that you're getting by going out over here is going to be at most the one that you're going to get by going all the way to the end. So that means that going all the way out to the end is always going to be optimal. So either you would go to the left end or you would go to the right end. You won't go out in between. So the path between any node, or the longest path between any node and a certain node and any other node is going to be one of the endpoints of the diameter, no matter which diameter that you choose. Yeah, and that's a very nice property. It can allow us to solve many problems. yeah, diameter. There are many ways to calculate. You can also calculate it by go too deeply into any of them because I ability to calculate. So now centroid decomposition is essentially a way to adapt divide and conquer onto a tree. So on a tree, let's say our tree looks like this. The centroid is any node where the subtrees, so the subtree is like this, like this, like this. No subtree contains more than half of the nodes. And in this case, 1 is not more than half of 4, which is 2. So this node is the centroid. And once we find the centroid, we can actually very easily, calculate like a lot of different really cool things. So, like it, yeah, first of all, it always exists because let's use contradiction. Let's say there's no centroid, right? Then let's start from a certain point, right? Dot, dot, dot. Let's say that the total amount of subtrees, the total subtrees outside of this edge, so there's things over here, right? The total subtrees outside of this edge is less than n over 2, but this side is greater than n over 2. But it would still be less than n over 2. And this would decrease. And as long as it's greater than n over 2, this subtree will never get up to n over 2. And once this goes and oh yeah, and then let's say that means that we can have this. So this has to be greater than n over 2. So these nodes all have to, where this has to be greater than n over 2. This subtree has to be greater than n over 2. So that means the combined amount of these subtrees must be, so like you have n over 2 and then minus 1, n or minus greater than n over 2, which is n over 2 minus 2. And n over 2 minus 2, if we move to this next one, plus this will keep decreasing and this will never, it will go less than n over 2. And even at that point, this will still not exceed n over 2. So there will always be a centroid. And that's exactly how you calculate a centroid, actually. You go up from a random node, and then you keep going until all of the nodes are less than n over 2. So, yeah. Yeah, so now let's explain how centroid decomposition works. So centroid decomposition works the following way. You essentially have the whole tree. Now you find the centroid. This is the centroid. Now you find all of the values within each different subtree. So here you find all of the values. You calculate all of the paths that go through the centroid. And then once you've done that, you mark this as visited. And once you've marked it as visited, you basically delete all of the edges from it. You don't really delete them. You just say like, if visited, just continue. And then after that, we have this smaller subtree and all of these subtrees. And because it's the centroid, all of these are less than or equal to n over 2. Which allows you to repeat the process until you're done. And from divide and conquer and the time complexity of divide and conquer, you know that this will go on for at most log n times. So this will be able to solve a lot of different problems. Yeah. Yeah, let's keep going. The next technique I'll talk about is heavy light decomposition. Heavy light decomposition is almost always overkill, but it's always nice to know how to overkill a problem because sometimes you can't think of the elegant solution, so you can just overkill it without thinking too much. So yeah, basically the idea behind this is let's say you have a node and what you do is you mark some nodes as heavy and some nodes as light. And you mark the node, or you don't mark nodes, you mark edges as heavy or light. And once you've rooted the tree, you can basically start from this node, and for each of the nodes, or for each of the edges that are going down from that node, the heaviest edge, or the edge that contains the subtree with the biggest size, is going to be heavy. So this one's heavy. And these are all light. What this allows us to do is this allows us to have a segment tree over all of the heavy edges. So for each chain of heavy edges, so if you look at your tree, if you look at your tree, if it used to look like this or whatever, it'll now look like a bunch of chains of heavy edges, essentially. And once you've broken it down into a bunch of chains of heavy edges, you can put all of them into a segment tree, and then you can find a range of them by just querying over the segment tree. So that's the way you find a range of heavy edges. So let's say you want to find a vertical path. Let's say a vertical path from here to like here to here. So how would you do that? Well, because you can find all of the ranges for all of the heavy edges, you only need to figure out what the light edges are. But you don't need a trick to figure that out, because they're at most log n light edges, since each one would at least double the size of its subtree. So there are at most log n light edges, which means there are at most log n streaks of heavy edges, which means our total time complexity for finding a vertical path is O of log squared n. And once you find that the time complexity is O of log squared n, you can just do a lot of different things with this. It's a very cool technique to know to overkill a bunch of problems without thinking too much. So yeah. This is the practice problem, but yeah, so there are two ways to solve this problem. The first way is to use the tree diameter methods that I described. It shouldn't be too hard. Like, this is a direct application, so I'll leave it to you guys to figure this one out. But I'll talk about the centroid decomposition method, because that one is much more interesting and it applies. Let's assume that we've added all the barns. So now we have the entire tree, and each time, instead of adding the new barn, we're just activating a barn, which it does the same thing. For two operations, we need to be able to activate a node, and second, we need to be able to find the longest path between that node and any other node. So the idea, the way we want to do this is we want to essentially use centroid decomposition. So yeah, let's say this is our centroid. This is our subtrees. And let's say our node is within here, and it is connected to the centroid, right? So first, we want to see if going through the centroid helps the answer at all, or like we basically calculate the answer of it going through the centroid. If it's not connected to the centroid at all, then literally we don't need to do anything. So we need to calculate, what if it's connected to the centroid? What is the maximum depth? Well, we can pre-compute the maximum depth in each of these subtrees. Remember that the centroid decomposition structure is completely static. So we can calculate the maximum depth, max depth, before we've done anything. We can calculate the max depth. Right? We've calculated the max depth of both of these. And now once we've done that, it's actually really, really easy, because we can calculate the max depth plus 1 plus the depth of that specific node, which we can already calculate. We can pre-calculate, or the max depth here plus 1 plus the depth of that node, which we've pre-calculated. So we can basically do this in log n per query with centroid decomposition. So now we just need to be able to activate a node. Well, in order to activate a node, we don't need to touch this subtree at all. Or let's say we're in here, right? We don't need to touch this subtree at all. This one, we don't need to touch this one. We don't need to touch this one at all. We just need to touch this one, right? And the way we do that is, let's say that node is connected to the nodes above it in the centroid. So like it's connected to the nodes above this, and that will connect to the centroid. And then once we activate this node, that means that we're giving this node a depth which is equal to the depth of the previous node, which is connected to the centroid +1. And then here, if it's connected to any other nodes, we can just say that, oh, hey, now it's connected and your depth is this +1. And we can do that in O of 1 per subtree. And once we do that in O of 1 per subtree, since there are only at most log n subtrees, we can do it in O of log n. So it's relatively hard to code. It's also very hard to conceive of. It's much harder than the tree diameter solution, which is really clean. But it shows you the power of centroid decomposition to solve this type of problem, even though tree diameter is so much more efficient. Yeah. So yeah, other useful strategies. Yeah, almost every topic is basically fair game. So you can never be able to master all of it unless you research it yourself, solve problems yourself. You won't ever be able to get all of your information from someone else. You're always going to have to, and even if you are able to get all of the information from someone else, you're not going to be able to properly apply it, properly understand it, unless you really read articles yourself, you really dive into some detailed, complex problems, and really only that can help you get better. So you should find what works for you, what's most efficient for you to help you improve, whether it's doing problems above your level, how much above your level, like should you do problems 500 rating above your level, or should you do problems that are 100 rating above your level, or at your level, or maybe even below your level? Who knows? But you should definitely do as many problems as you can, because each problem that you do means it's another skill that you know, it's another pattern that you've recognized. It's another way to build that, I guess, muscle memory, or I guess like your memory of how you're going to be able to solve a certain type of problem. Another thing is doing problems that are targeted. Like, for example, if you're struggling at dynamic programming, maybe you want to do a lot of dynamic programming problems, or you might want to say, oh, I want to like be able to figure out all of the intricacies of every problem. I don't want to be told this is dynamic programming problem, please solve it. Then you might be more efficient when you're doing just like random studying, because you don't already know what the topic is about, what to think. So that's another thing. There's a lot of different nuances about how to train, but these are just very broad pieces of advice. Also, every point counts, every single one. I can't stress this enough. USACO people always look for your ability to gain points from subtasks. So you need to solve subtasks every time. You can't just rely on full solving a single problem, because that won't be good enough. You can get like 100 or maybe even 200 points from just solving subtasks in a problem. So if you can, get as many points as you can. Another thing is, use your time wisely. If you've spent an hour on the first problem and you still haven't made any progress, maybe stop trying the first problem, maybe try another problem, then get back to it with a fresh mindset, not trying the exact same thing that you tried the last time. There's a lot of different yeah, there's a lot of different nuances to contest strategy as well. I won't get into that too deeply either, but just know that you should try to get as many points as you can. And managing your time is very important, especially if you're not aiming for 1,000 points. You're not expecting to get 1,000 points. You are aiming for like 400, 500 points. And to do that, you need to manage your time very, very wisely. You can't just solve every problem because you won't be able to, right? So yeah, this correlates to the previous slide about contest strategy. Just know that getting into camp for the first time requires you to only solve about one problem per contest. For me specifically, this year, I got scores of 167, 416, 272, and 410, and that was good enough to get into camp. So you're not trying to get 2 or 3 problems to get into camp. No, that is way too high. You need to set a goal of being able to get one problem plus like subtasks on the other 2 problems, so that you can guarantee that you are able to, do well on each contest. Yeah. Yeah. So yeah, these are a bunch of practice problems that I found. I can a bunch of practice problems that I found. I can also no, I don't think actually I'll make this final note. Essentially, in Platinum, your math foundation needs to be very, very, very strong in order to succeed. You need to be need to be very good at math in order to be able to succeed in Platinum, because for example, like in many cases, math can help you find observations. Sometimes the problem is blatantly just math. Sometimes the problem requires you to know some math optimization, like a simplification of a certain type, or whatever, matrix multiplication. You could require eigenvectors, eigenvalues. You could require a lot of different mathy things. And if you're not good at math, it's very hard to succeed at this level. So you need to have a decently strong foundation in math. Another thing is, like in a lot of geometry problems, they'll require like very intricate math and very intricate like convex hull, whatever, a lot of things can be solved with just like mathematical intuition. So yeah, that's basically the note I wanted to make. Like just like you need to be very good at math in order to succeed at Platinum. Yeah.